Welcome to my video on using Hooke's law to measure a spring constant. Before we actually do the measurement of the spring constant, we need to talk a little bit about Hooke's law and what that is. Hooke's law describes how an elastic object, like a spring, responds to a force that tries to stretch or compress it. Hooke's law states the force needed to extend or compress a spring by some distance is directly proportional to that distance. So you can see in this diagram here, the larger the weight, the more the spring extends, and that's due to the weight, which is mass, and then the force on that is mass times the acceleration of gravity, which is 9.81 meters per second squared. So that's the basic idea of Hooke's law. This slide, I'm going to look at Hooke's law in more detail. The force is equal to minus kx, and where k is the spring constant, that's what we're trying to measure in this experiment. And then the force is this is the force in newtons, and this is displacement. So force is applied to a spring in newtons. It can either be a compression or an extension. And the spring constant is dependent on the type of spring and how it's made and the material used in the spring. So k is a spring constant. It measures the spring stiffness, and that's in newtons per meter. That's going to be the units of that constant. And x is the displacement of the spring from its rest position, and this is going to be in meters. Now the negative sign indicates that the force extended by the spring is opposite the direction of the displacement. It resists deformation. So in other words, when we pull on a spring, try to extend it, the force back on the spring tries to move it back towards the equilibrium position. This would be the equilibrium position. It's just sitting there, not moving. And if we try to compress the spring with our hand, it's going to exert a force outward to avoid the compression. So that's what springs naturally do. And Hooke's law just relates this mathematically. And what I want to do here is show you the experiment that I used, or the way I measured the spring constant. Basically what we've got is the setup here. I've got a stand, a ruler measured in centimeters and millimeters. Here's the spring we're going to measure. This little thing is just a little marker. And then this is a device here that I use to add the weights. And I've measured the weights. They're 10-gram weights each. And I double check that with a gram scale. So I feel that's a pretty accurate number. So I'm going to step through this measurement and just explain each step to you. Okay, so the first one we've got is, this was the displacement. It was 13.4 centimeters. Now I added the first weight. It caused it to extend a little bit further. I waited till everything stabilized, 14.4 centimeters at 10 grams weight. Now I added another 10 grams to it. It extended down a little bit further, additional force. For 20 grams, I got 15.4 centimeters of displacement. Added another weight. I actually had a little trouble there. So now we have 30 grams on it, and we have a displacement. I'll wait till this stabilizes. You'll see a glitch in the film. There we go, 16.4 centimeters. Now I added another problem there. These things are kind of small. And 4 weights, which is 40 grams. And wait till that stabilizes. Then I measured 17.3 centimeters. And finally I added a 5th 10-gram weight. And the final displacement, let's wait for it, was 18.3 centimeters for the 50-gram weight. Now the results of this, as you just saw in the video, the column to the left here gives us the mass of the weights that I added. So I added 5 10-gram weights to get up to 50 is the maximum. I measured the displacement in centimeters, so with 0 mass attached, it was displaced at 13.4 centimeters. That's our 0 point. Now on this line, I calculated the extension, and this is going to be in meters. So when I convert to meters, I take the number of centimeters, I divide by 100, and then I subtracted off the 13.4 because that's sort of the starting point. So this is the displacement in meters away from that 0 point of 13.4 centimeters. Now in this last column, I calculated the force, which is the mass times the gravitational acceleration. It's going to have units of newtons. And so what we need to realize here, here's the gravitational constant of acceleration, that's in meters per second squared. And now we had to convert this to kilograms because the units of newtons were going to require kilograms. And so I had to divide the number of grams by 1,000. So this is the force downward on the spring due to the weight and gravity and expressed in newtons. And this is going to be the extension of the spring from the 0 point in meters. Now I graphed it out. That graphically gives us a much easier way to determine. So here's the force in newtons, and here's the displacement. And so you can see the slope of this is going to be going to give us this constant right here. That's going to be, I did this in Excel, plotted those points, asked it to do a line, best fit line, and then it also gave me the equation of that line. And so you can see there's a small 0 offset, that's okay. We're very close to 0. And so that turned out to be the slope. And we'll go through that. Okay, so for measuring the spring constant from the slope of the line, it turned out to be 10.0 newtons per meter. So that was the spring constant. Now in this measurement, we've got major sources of error was our displacement. You can see it was not super accurate, but it's probably good to plus or minus 1 millimeter. I did let things stabilize, so we got a good measurement. And also the spring is not perfectly linear. It's just a spring, it's a mechanical spring. Well, I hope you got something out of this video, learn a little bit about Hooke's law and measuring a spring constant experimentally. And thank you for watching.